Welcome to AP Physics C, Capacitance. Capacitors are devices that can store electrical energy. Unlike batteries, capacitors are able to release a large amount of energy in a short period of time. For example, when you're taking a photo, the photo flash are able to emit a large quantity of electrical charge in a short period of time. So how do we define capacitance? In physics, we define capacitance as the ratio between electrical charge and electrical potential. The unit for capacitance would be Coulomb over watts, or farad. As you can see in this graph, one way to charge a capacitor is to place it in an electric circuit with a battery, as shown in the graph. An electric circuit is a path through which charge can flow. A battery, of course, is to maintain a constant electric potential, whereas this is a capacitor. As the photo illustrated, all of these are examples of capacitors, and they have different geometric shapes. And later on, we will discuss about how different geometrical shape can change the capacitance value. Alright, so in this video I will address three types of capacitors: the parallel plate capacitor, cylindrical capacitor, and spherical capacitor. I will also talk about capacitors in parallel and in a series circuit. Alright, parallel plate capacitor. There are two metal conductors. The top one is negative Q. The bottom one is the top one is positive Q. The lower one is negative Q, and the distance between them is D. The area of each of these plates is A. Alright, so we'll do some math here. According to Gauss's law, we know influx equals to E electrical field times area, which in this case is just A, equals to Q over epsilon naught. And Q is the electrical charge it can carry. So from this equation we can derive Q equals to epsilon naught times E times A. A is the area, whereas the E is the constant electric field between the two plates. Alright. From the last chapter, we know electrical difference, electric potential, is equals to the integral from negative to positive E ds. And the negative and positive are just artificial definition. We defined it. And this equals to ED. Alright, we need more space. If you can still remember, we defined capacitance as the electrical charge over the electric potential, C equals to Q over V, which then equals to epsilon naught times EA. And how do we get it? It's from here. Divide by electric potential, which can also be written as ED. So from this, we clearly see the electric field cancel each other, and all we get is the epsilon naught times A over D. And since epsilon naught is only a constant, the value of capacitance solely depends on the value of area and the distance between the two plates. It's a very neat equation. Alright, we'll see some problems. Alright, exempli gratia. Number 1. This question, alright, first let's look at the graph. The graph is an electrical charge and electrical potential graph. As you can see, there are three capacitors, And the area of each capacitor in the separation as is shown in the graph. It's showing in the table. And it's asking for identifying which one is A, which one is B, and which one is C. So we will the first step towards solving this problem is by recognizing E over V is capacitance. So the slope of this graph is Q over V, electrical charge over electric potential, that equals to capacitance, and that is the slope. It's like Y over X. The slope is represented by this graph. And we clearly see capacitance A is bigger than capacitance B, bigger than capacitance C. And we also know that capacitance equals to epsilon naught times area over distance. So we can rewrite, using the table, the C1 equals to A over D epsilon naught. C2 equals to 2A over D equals to times epsilon naught. C3 equals to A over 2D epsilon naught. And from this, we derived that C2 is bigger than C1 is bigger than C3. And since CA bigger than CB bigger than 3, and C2 bigger than C1 bigger than C3, then we can conclude A is 2, A is 2, B is 1, C is 3. Alright, let's see another example. The problem goes like this. A parallel plate capacitor has circular plates of 8.20 centimeter radius and 1.30 millimeter separation. The first part is asking calculate the capacitance, which is easy, and then find the charge for a potential difference of 120 volts. How would we solve this? We're starting like this. Capacitance equals to Q over V, also equals to epsilon naught times A over D. And since we know it's a circular plate, and the area would simply be pi r squared, 0.082 square times epsilon naught divided by 0.0013 meters. And that, according to my calculator, will give me 144 pf. Good job. B. Find the potential difference. No, find the charge for a potential difference of 120 volts. So the charge would equals to capacitance times electrical difference, which is going to be 17.3 nano coulomb. Let's see. All right. Cylindrical capacitor. We will need more math here. So first of all, I want to point out in cylindrical capacitor, we assume L is a lot bigger than B. B is the radius, the outer radius, and A is the inner radius. The inside cylinder has a positive charge, whereas the outside cylindrical capacitor has a negative charge. And we are integrating from inward, radially inward. All right. So the reason why we assume the length of a cylindrical capacitor is way bigger than its radius is because we can neglect the electric field at the two ends. All right, let's do some math. Q equals to epsilon naught EA, as I had shown in the previous slide, and this equals to epsilon E 2 pi L 2 pi L is A. It's a surface area for a cylinder. And Q, excuse me, then E simply equals to Q over 2 pi epsilon naught L R. Why do we need the electric field? Well, because we need to find electric potential. Electric potential equals to negative to positive E ds. And in this case, since we're integrating radially inward, ds would equals to negative dr. And this integral will equals to the integral q minus 2 pi epsilon naught dr over r. And this gives us q over 2 pi epsilon naught L, oh I forgot L there, sorry, times ln B minus A. Capacitance equals to Q over V, electric potential. And if you do the math correctly, you will get 2 pi epsilon naught times the length over ln B over A. So as we can see, these are all constant. The value of capacitance solely depends on the length and the ratio of the inside and outside radius. Alright, let's move on to spherical capacitor. Very similar math. We have Q equals to epsilon naught EA according to the previous slide, which equals to epsilon E times the surface area for a sphere would be 4 pi r square. Excuse my handwriting and this terrible template. 4 pi r square. And the electric field would equals to Q divided by 4 pi epsilon naught r times minus 2. If we integrate this for electric potential from negative to positive, ds, this will give you negative Q over 4 pi epsilon naught from B to A. And be careful, the reason why we have minus sign here, because we're integrating from outside inward radially. And that's why we have the negative signs when we change from ds to dr. So I'll mark here ds equals to negative dr. Same reason as the previous slide. And then we have dr over r square. This should give us something like Q over 4 pi epsilon naught times B minus A over AB. Alright, so since C, the capacitance equals to electrical charge over electric potential, which equals to 4 pi epsilon naught times AB minus B minus A, if you did the math correctly. So 4 pi epsilon naught is a constant, and the only thing that can affect the value of capacitance is what? Is the radius of the two spheres. Alright, question number 4. The plate of a spherical capacitor has radius 38 mm and 40 mm. Calculate the capacitance and what must be the plate area of a parallel plate capacitor with the same plate separation and capacitance. Alright, so what we do is, for spherical capacitor, we have capacitance equals to 4 pi epsilon naught AB divided by B minus A. In this case, B would be 40 mm since B is always the one that is bigger, and we will get 84.54 p farad. Alright, first part. The second part. The second part is actually even easier if you know how to do it. So we have epsilon naught times AD. That's the capacitance for a parallel plate capacitor. That equals to epsilon naught times 4 pi AB divided by B minus A. And as you can see, epsilon naught canceled each other. And since D simply equals to B minus A, in this case, D and B minus A also cancelled. So the area is simply 4 pi times AB, which is 191 centimeters square. Alright. So the last part of the video I will address about when you place a capacitor into a parallel circuit or into a series circuit. What would we do? Alright. So first one, we'll talk about parallel capacitors. So in this case, it reads like capacitors connected in parallel can be replaced with an equivalent capacitor that has the same total charge Q and the same potential difference V as the actual capacitors. So how to interpret that? So we can see in this graph showed that the A is equivalent to B because all the electrical charge, if you add them all together, they will equals to the electrical charge net, the Q net. Whereas the electric potential everywhere is the same. And that's very important because that's how we find the relationship between capacitance net and each of the subcapacitance. Alright, let's do some math. Q1 equals to C1 V, Q2 equals to C2 V, Q3 equals to C3 V. Why do I have the same V? Well, it's because they all have the same potential difference. And the total electrical charge is the same. So Q equals to Q1 plus Q2 plus Q3. Electrical net and all the each electrical charge for each part of the circuit. If you add them together, you will get C1 plus C2 plus C3 V. And we know C for the circuit would equals to Q over V, and that equals to C1 plus C2 plus C3 by doing the math. The conclusion is this. Bing bing. The total capacitance is just simply the sum of all the capacitance for the parallel capacitors, for each parallel capacitors. Alright. How about the series capacitor? Well, for series capacitor, capacitors that are connected in series can be replaced with an equivalent capacitor that's the same charge Q, unlike the parallel capacitor, which have the same potential difference V. Now we have the same charge Q and the same total potential difference V as the actual series capacitor. So it's just flipped comparing to the previous case. Now let's do some math. V1 equals to Q over C1. V2 equals to Q over C2. V3 equals to Q over C3. Why do I have the same Q? Well, because it said all the capacitors, all the series capacitor have the same charge Q. They all carry the same charge. And that is concluded from doing experiments in circuits. Alright, so we have V1, excuse me, we have V equals to V net equals to V1 plus V2 plus V3, and that equals to Q times 1 over C1 plus 1 over C2 plus 1 over C3. So 1 over the total capacitance would equals to V over Q according to the fundamental theorem, and we have 1 over C1 plus 1 over C2 plus 1 over 3. So what is the relationship? This is the conclusion. The capacitance, total capacitance, is 1 over the total capacitance equals to the sum of all the inverse series capacitors in the circuit. All right. I hope you enjoyed my video, and please feel free to ask me any questions or send me an email if you wish, and good luck.